The last kind of problem I want to look at in this applications chapter has to do with the center of mass, which will also be known to us as center of gravity and will also be known as the centroid. Before we actually get going on that, force is not mass, as we've said before, but if you're near the surface of the Earth, weight, which is the force due to gravity, which is measured in pounds or whichever system of measurements you're using, is the acceleration due to gravity times the mass, which is in kilograms or whatever units you're using. As long as you stay relatively close to the surface of the Earth, the g is roughly constant. It's roughly 9.8 meters per second squared, or 32 feet per second squared. A reasonable question is to ask, if you change your distance from the center of the Earth by a little bit, how much does the acceleration due to gravity change? So before we get going, I want to look at that. The acceleration due to gravity is Newton's constant times the mass of the Earth divided by the square of the distance to the center of the Earth. When we're on the surface, we're about 6.4 million meters from the center of the Earth. I'm going to estimate how much this acceleration changes as I change the x by looking at its derivative. It's easy to figure out that the derivative of a with respect to x is negative 2 gm over x cubed, which means the change in acceleration is approximately negative 2 gm over x cubed times how much you change the x. If you factor that up, you get negative 2 multiplied by gm over x squared times delta x over x. This is very convenient because gm over x squared is the acceleration due to gravity. Delta x is the amount that you changed x by, and x is roughly 6.4 times 10 to the 6 meters. I want to think about delta x being about 100 meters. This is the general type of scale that human beings deal with on a regular basis. If I change the height from the center of the Earth by 100 meters, how much does the acceleration due to gravity change? We'll get this by doing our differential approximation here. So I put the numbers into my calculator. Over a vertical range of about 100 meters, the acceleration due to gravity decreases by about 0.0003 meters per second squared. And remembering that the acceleration itself is about 9.8 meters per second squared, that's practically nothing. On these kind of distance scales, the acceleration due to gravity changes so little that you might as well pretend that it's a constant value. So over these distance scales, the weight of an object, the force that gravity exerts on it, is basically a constant multiplied by the mass. That is to say, if you double the mass, you double the force. If you triple the force, you triple the mass. And for our purposes, we can, roughly speaking, treat these numbers as interchangeable. So I'm not going to worry about whether it's pounds, which is a force, or kilograms, which is a mass, or newtons, which is a force, or slugs, which is a mass. I can use these words more or less interchangeably in pairs. I want to think about taking a lightweight piece of plywood, and by lightweight, I mean so lightweight that I can ignore the mass of it. I'm going to glue this mass to a piece of plywood, and I'm going to try to make a balance out of it. So we'll have the fulcrum here Now, obviously, if I make the mass that I glue to the piece of plywood to the right of the fulcrum, the thing is going to turn in a clockwise direction. If I put the mass to the left of the fulcrum, the thing is going to turn in a counterclockwise direction. The prototype for this sort of thing would be a seesaw. So one thing I could think of doing would be to take a 10-pound weight and attach it to this lightweight piece of plywood 5 feet out from the fulcrum on one side. This will tend to make the thing turn in this direction, clockwise. I can take a 10-pound weight and put it 5 feet out on the other side. That'll tend to make the beam rotate in the opposite direction. And since the weights are the same, we'll achieve a balance there. We'll achieve an equilibrium. Of course, having done seesaws and stuff, you know that's not the only thing you could do. You could put a 10-pound weight 5 feet out to the right of the fulcrum, and if all you had available was a 20-pound weight, you would just put it twice as close to the fulcrum. You would put it 2.5 feet to the left, and you would get balance then. So the first idea that you need to get in the back of your head is the influence of an object to make this thing rotate one way or the other basically is going to be its mass times how far out from the fulcrum it is. Or, since we're treating mass and weight more or less interchangeably, the weight times how far out you are. Of course, we need some way to keep straight clockwise versus counterclockwise so that we'll know how to correctly account for all of the contributions. So imagine I try to balance this thing at x bar equals 3, and I'm going to have two masses. One of them is going to be located 4 units to the right of the fulcrum, well, 4 units to the right of 0, that is. Since x bar itself is 3, this distance is only 1, and my mass that I'll associate with that is 10. This is going to tend to make the thing rotate in the clockwise direction. The measure of this is going to be the mass times the distance, which is 10 times the distance between 4 and 3. This is going to contribute 10 units of contribution to making the thing turn clockwise. On the other hand, if the second mass is 9 and x2 is at -1, then you've got 3 units of distance from x bar equal 3 to 0, and then you've got another unit of distance to get to -1. x2 is 4 units to the left of x bar. The contribution is going to be mass times distance, which is 36, but I've got to keep this straight. This contribution tends to make the thing turn this way. This contribution tends to make it turn the other way. What we'll do is we'll give these numbers positive or negative signs depending on whether they contribute to a counterclockwise motion or a clockwise motion. So literally, not worrying for the moment about the direction, the contribution is going to be the mass times the distance from the location of that mass to the fulcrum that I'm trying to do. Notice that if I do it this way, if I do mass times coordinate minus fulcrum, things take care of themselves automatically. If xi is bigger than x bar, like it is in this picture, then xi minus x bar is going to be positive. The mass times that will be positive, and I'll associate positive contributions with motions in the clockwise direction. On the other hand, if I had an xj mj and the xj were smaller than x bar, then xj minus x bar will be negative, the mass times that will be negative, and I'll get a contribution that contributes to a rotation in the other direction. So these numbers, I'll rely on whether they're positive or negative to tell me how they contribute to the motion of the entire system. So this summarizes the verbal description that I just gave. So if I have a whole bunch of objects with masses m1, m2, m3 out to m number n, where n is the number of things I have, and they are located at x coordinates x1, x2 out to x number n, if I want to look at the total contributions from all of the individual pieces, I'll do m1 times x1 minus x bar plus m2 times x2 minus x bar, and I'll just keep adding all of them up until I've added in the last one, m number n times xn minus x bar. If this quantity is positive, then the overall motion of this beam is going to be in this direction. It's going to be clockwise. And if this number works out to be negative, the overall motion will be counterclockwise. Now, of course, this depends on the masses. It depends on where they're located at, and it depends on this number x bar that I'm trying to analyze here. If I want to make x bar the place where the system balances, where the negative contribution is exactly canceled out by the positive contribution, I want that quantity that I just calculated to come up 0. I want to find this x bar that will make this happen, and because we're treating weight and mass more or less as equivalent, the words center of mass, center of gravity, centroid all mean the same thing to us in our application. This is the x bar value that makes this sum equal to 0. Do some algebra. That first term is m1x1 minus m1x bar. The second term is m2x2 minus m2x bar, and so on and so forth. When you write it out like this, you get a bunch of terms, some of which have x bar in them, and some of them don't. So multiply all of this stuff out, and all the terms that have x bar in them move over to the other side of the equation. If you do that, good things happen. Over on the right-hand side of the equation, every single term has exactly one factor of x bar in it, so you can factor it out. Over on the left-hand side, you are adding up the masses times their coordinates. Masses times coordinates, add all of that up. It's equal to x bar times the sum of all of the masses that you're talking about. Divide through by the sum of the masses, and you've got a formula that tells you where the center of mass is going to be. The x bar that you're trying to find is a fraction. Upstairs, it's the sum of all masses times coordinates. On the bottom, it's just the sum of all the masses. For obvious reasons, we call the bottom of the fraction the total mass of the system. And upstairs, people have given that sum of masses times coordinates. They call that the moment of the system. So you can imagine that you've got some very lightweight beam of plywood and you glue three masses to it. One of them is located at x1 equals 4 and has mass m1 equals 6. The second one, x2, is -1 and the corresponding mass is 8. And the third one, x3, is 2 and the mass of that one is 1. If I want to figure out the center of mass, I take each point, I multiply its mass by its x-coordinate, and add up all those things. On the bottom of the fraction, I add up the masses, which would be 6 plus 8 plus 1, and after you do the arithmetic, it works out that x bar is 1.2. So the place where this fulcrum should be located on the number line, represented by the lightweight beam, is x bar equals 1.2. If you put your fulcrum there, there'll be exactly as much clockwise tendency as there is counterclockwise, and you will have found the balance point. Next, imagine that you've got a two-dimensional piece of plywood. You've made it so thin and lightweight you can ignore its mass, and then you glue various objects to it. Each one of the objects will have an x-coordinate, a y-coordinate, and of course, each one of the objects will have a mass or a weight, depending on how you want to state it. Somewhere in this region, there's a place where you could balance the thing, where it would tend neither to go in the positive or negative x direction, or positive or negative y direction. We're going to need two coordinates to describe that, so I'm going to call the balance point x bar, y bar, and the calculation that we end up doing is pretty much the same as the other one. If I have the balance point, I don't want the thing to go this way. And this situation is what we've looked at before, except we have a new variable. Also, besides not wanting to go this way, I'm not going to want to go this way either. And that is exactly what we've calculated already. So treating the two coordinates independently, we're going to have for this one, masses times distance from the y-axis. That is to say, masses times x-coordinates. And in this one, we'll have masses times y-coordinates, which are the distances out from the x-axis. So if I calculate this quantity, this is the tendency of my system to rotate about the y-axis. If I calculate this quantity, this is the tendency of my system to rotate about the x-axis, keeping in mind that these x-coordinates are, at least up to a sign, how far out from the y-axis I am. And the y-coordinates, when I calculate y bar minus yi, except for maybe a sign, that's how far out I am from the x-axis. This explains some rather odd naming conventions that we'll see in a second. I want the tendency of my system to revolve about either one of those axes to be 0. So if you go through exactly the same algebra that we did before, you find out that the balance point is going to be given by x bar equals this formula, which if you look at it, is exactly the same formula we had before as it should be, but there's more to it. The y-coordinate of the center of mass is going to be given by this formula. Naming conventions are, we call the bottom of the fraction capital M, which is sensible enough. It's the total mass of the system. These numbers are masses times how far out from the y-axis I am. So people bizarrely call this the moment about the y-axis for that reason. These things, the masses times the y-coordinates, those are the masses times how far I am out from the x-axis. So for the same reason, people call this the moment about the x-axis. If you think that these naming conventions are rather strange, you're not alone. An easier thing to do if you don't want to keep that straight is to keep these straight in your head, and there's no chance for confusion then. So like before, a simple example with 3 points. I'm going to have my first point having mass equal to 10, and the x and y coordinates of that point, x1, y1, will be 3, 1. My second point will have mass 8, and its location, x2, y2, is 5, 9. The third mass has 4 units of mass associated with it, and its coordinates are going to be 10, 0. That's x3, that's y3. If I want to calculate the center of mass, it's a simple thing. The x-coordinate of the center of mass, I've got to calculate the sum of the masses times the x-coordinates, and then divide that number by the total mass, and this works out to be 5 after you do all of the arithmetic. In a similar way, the y-coordinate of the center of mass, y bar, is the sum of the masses times y-coordinates divided by the sum of the masses. Do the arithmetic, it turns out that y bar is 3.72 repeating. The center of mass is x bar, y bar is 5, 3.72 repeating. If you glued these 3 masses to a very lightweight piece of balsa wood or something, this is the point where the thing would balance. Either the one-dimensional or two-dimensional systems we've looked at have only a finite number of points to them. So for that reason, they're called discrete systems, finite discrete systems. What we really want to talk about, and what's going to be in the next discussion, is this. What if you had a region in the plane? It might be shaped something simple like a rectangle or a triangle, or maybe some other complicated shape. Imagine that object having a certain mass density to it, so many kilograms per square meter. Somewhere in that region, there's a balance point. There's a place where you could put a fulcrum and have the object be in equilibrium. We want to calculate that kind of center of mass, and we'll call it a fancy name, centers of masses for planar regions of uniform mass density. That's what's coming next. In the meantime, I hope everyone's having a good day. I'll talk to you again soon.